so now our unit 7 lesson 2, okay? Relationship between two quantities. So it's just kind of the idea between x and y. So relations, much mathematics involves a search of patterns, relations between two sets of data, your input, your output, your x, your y, okay? They also do time and distance or time and height. A lot of different things can be related, but most of the time we're talking about x and y. Okay, for the example, the value of a computer is related to its age. Okay, so how old it is, less value. The price of the watermelon is related to its weight, heavier the more expensive. And the time taken for a person to walk to school is related to distance to be walked. Okay, so list one more example of relations. So what's something that's a relation? What do you got, Chris? Give them up a relation.
Well, just the amount of something, like if you're buying something, like the amount of how much you're buying, the cost can go up.
Okay, so like number of items that you would buy? Okay, so number of items to total cost. Okay, let's see if we can get a couple more here just to do a lot of different things. Taylor, you have anything? How about a hockey one? More shots means more, number of shots to goals. Okay, Josh, you have anything? What can be related?
The more weight you lift, the stronger you are.
Okay, so more weight, more muscle.
Yeah.
Okay, probably have a little argument in physiology there, but we can kind of go with that. Because certain people are explosive, but they're not super muscular. There's a lot of people that are strong that aren't huge. Okay, got anything? Any final one?
You could do like volleyball serve or volleyball points.
Okay, so the more you serve, the more points you get. More serves, more points. And we have a really good one that I just want to share before we move on. No? Dang. Okay.
Do you have a good one for us?
I think, well, just because of what we do in Math 20, a good one is time and height. So, like, if I throw a ball to Jad, the height of the ball will be related to the time it's in the air. So those things are related. So, like, if I throw, like we were doing our thing today, yeah. So, and if I threw something to Jad, Jad's going to catch it at a point. Like, maybe it takes 2 seconds to get to Jad. So where is that at 1.2 seconds? That height would be the relationship. Okay, an idea? Okay, good. All right, so we're representing the relationship between two quantities. In this unit, we'll consider 7 ways in which a relationship can be between two quantities can be represented. In words, so these are 7 different ways we can do it. We got words, table of values, set of ordered pairs, so that's the points, mapping, like a diagram, an equation relates things, a graph, and then function notation. Okay, so there's 7 different things we're going to talk about. Function notations like an equation. We'll talk about that when we get there. Okay, so investigating a relation. Okay, consider the following relation. The cost C, cents per kilometer, of driving a car is related to speed S kilometers per hour, which it is driven. We use this relation to introduce some ideas which will develop throughout the course of this unit. This example illustrates a relationship between variables C and S. So we have cost is related to speed. Okay, so like what that means is how fast you're going is going to be kind of how much gas you'll burn faster, right? The more gas you burn, the more expensive your trip is. Okay, the statement, let's see here. C is called dependent variable. So why is C dependent? What does C depend on? Cost depends on the speed. Yeah. Cost depends on the speed. When representing a relationship, we often regard the values of the independent variable as an input. This is what I was talking about, X and Y. Okay, we're talking about input, output, okay? X is your input. Output is Y. Okay? Input X, output Y. Input's your independent, N, right? Output is your dependent. We're representing a relation. Okay, before considering how to represent this relation, we need just some data. We need input values and output values. So the input values make the domain. Okay, so let's don't let me just gloss over that. The input values make the domain. So input values being what? Your X value, your independent. For this problem, your speed. Okay, so what I want you to get out of this, now stay with me. Domain goes with X. Range goes with Y. Domain means what can I try? Range is what can I get? Okay, what can I plug in? Okay, so for example, if we did domain of speed of a car, what is the domain of speed of a car? Let's say, I'll give you a max speed. The car can go at 220 kilometers an hour. Okay, that's the max speed. So what is my domain? If I wanted to say I can go between this speed and this speed, what would it be? Good, 0 and 220. Why is it 0? Why can't I have negative? Yeah, you can't have negative speed. That'd be interesting. Okay, so you can't have negative speed. Okay, so your domain, your possible speeds are between 0 and 220 for that made-up example. Okay, then your cost would be what those put out. So if I'm going 0 miles per hour, what's my cost probably going to be? 0. If I'm going 220, my cost might be, let's just say, $30. So my range is 0 to 30. Okay, so your range is your output, like what it can be. Your X is what you can plug in. Does that make sense? A little bit? Allie, no? Yeah. Okay, it's all right. We're just kind of setting things up, so don't stress yet. All right, so now we're doing, obviously we would not attempt to collect the data for every possible input, because especially on a continuous one, okay, especially on a continuous one, there'd be infinite things to try. We don't want to try an infinite amount of things. Okay, suppose we choose input values of 20, 30, 40, up to 120. Okay, so there's my table, one of the 7 things. Okay, diagram shows the information collected represented in ordered pairs. Okay, so your table, here is your X, here's your Y's. And they just took these and they just made them points. There's your ordered pairs. Okay, then they took those and they plotted them. Okay, is everybody okay still? Okay, and then the mapping diagram. Okay, mapping diagram we don't use a ton, but I'll explain it to you this way. It's just, all it is putting things in order. So 20 to 120, 7.5 to 10. So 20 is my slowest speed. So it gives me my, what is that, 10 cost per kilometer? Oh, that's interesting. So this, when you're going slow, so there's kind of an ideal speed. Do you guys see that? Looking at the graph, I'm just learning this one too, right? So when you're going 20, it costs 10 cents per kilometer, I believe. And when you're going 120, it also costs 10. So that means there's an ideal speed for you to maximize your money. Okay? Because this is why. Think about it logically. If you're going 20 kilometers an hour, what's the thing that's going to make it cost more? Why is it going to cost more for 20? It's going to take longer. Okay? So if you're going 20 kilometers an hour, you're going do-do-do, driving around. You drive for like an hour. Okay? Well, if you go 120, you're going 6 times faster. You'll be there that much faster. Your time would only be a sixth of what you did for 20. That's why there's a medium. That's why kind of something in the middle looks like 7.5. 70 kilometers an hour is your ideal speed. Okay? So you're not spending as much. Does that make sense, guys? Okay? So I was saying right here, the mapping diagram, we have 20 and 120 both go to 10. Okay? We'll get into what is a function, what is not a function later, but the mapping diagram is just mapping. We have 1, 2, 3, 4, 5. We only have 6 different values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 6 different values, so it's kind of symmetric. This one's the same, that's the same, that's the same. Okay, so just mapping your speeds to the price. Any other questions on those yet till we get to the next page? Okay. All right, so they give us the equation. So let's go through this here. We've only chosen some of the possible input values. However, it's obvious that an output value has been determined for any input value greater than 0. So we know they're not going to have 0, and not going to be negative. Later we'll learn how this can be done in a form of equation. So the graph of the equation of the relation is given below. Note the equation is only valid for certain input values which make up the domain of the relation. So that means that our domain was from 20 to 120, right? So that's our only input values we can have. Okay, and we want to figure out would not be valid for 5,000. It means we can't go 5,000 kilometers an hour, which I think that's understood. Okay, so the equation, they give this to us in a quadratic. We know it's called a quadratic from our factoring section. Okay, if you put that in your calculator, which we all have our graph calculators, you would get that parabola thing. Okay, you could change your graph so that it had these labels if you wanted, but it's not crucial. Okay, can anybody explain to me what makes this a parabola based on our table? Why is it curved? Think about the ends. When we were at 20 kilometers an hour, we had what? 10. And when we were at 120, we had what? 10. So it curves. So right here, now, would you describe this parabola as a valley or a hill? A valley. Do valleys have low points or high points? Low. Now, see, this is where it's kind of interesting. This represents our what? Your lowest point, but think about this problem. What does it represent? Say it one more time. Most efficient or lowest cost, right? This point represents our lowest cost. It's the minimum of our parabola. We're not getting to parabolas, guys. That's Math 20 stuff, but you need to kind of understand that now. Look at this picture, the bottom of the valley. That's my lowest possible price point. This is my minimum value, they call it. Okay? It's minimum because it's the lowest at 7.4. I think it's 7.4 or 7.6, I don't remember. 7.5, okay, so I was close. So it's right here. Okay, so it's just the lowest point, just something to point out. All right, next one here. Stop me if I say something you don't understand. I'm trying to swing through. We run out of time a little bit. Okay, independent, dependent variables in relations. So we kind of talked about that. So the values of independent variables represent the inputs, your x's. We've already talked about that, so we'll kind of skim through this. You have right here, your dependent variable is the output. This right here creates an input. So if I plug in 2, for example, 3 times 2 minus 5. What's 3 times 2? 6 minus 5. 1 would be your output. Okay? So in that graph, let's put this together. I give an input of what? 2. What did I get that came out? 1. This point, 2, 1, is on that line of that graph. 3x minus 5, the point 2, 1 lies on it. Okay? Where's the graph? Well, we haven't done one. If we did one, it'd be on there. Okay? Because if you plot the point, that's what you'd get. So if we did one more, saw some confused faces. If I plugged in 5 here, what's 5 times 5? Or excuse me, I said that wrong. 5 times 3, sorry. What's 15 minus 5? So another point on that graph is 510. Yeah. You have a question or your show? It's okay. Anything? So that's just, I'm just relating the points to the equation, to inputs and outputs, to that's where it would be on the graph. Okay, I was trying to kind of connect it all a little bit together. Okay. All right, so let's see what else they say here. Values of dependent variables represent the outputs. We know that. These are on the vertical axis, which means these are the y. They're the up and down movement of your point. So like 10, be 10 up. Okay. Values of independent variables are the inputs. We know that. And then it's on the horizontal axis, so 5 would be left. So it'd be 5, 10. We'll say this is 10 here. Okay, so 5, 10. All right, let's get to some examples here. Might have to break this one up. We might make it. All right. Okay. Oops, wrong stuff. Alright, so the diagrams show relations expressed in different ways. In each case, 1 states an independent variable, 2 states a dependent, 3 lists the inputs, 4 lists the outputs. Okay, so part A. What is my independent variable? I, 2, and 4. Okay, so where are we at? I think we're at Molly. Molly, what's my independent variable for part A? Which one's independent? P. Good. And then which one's dependent? Okay, good. And Janae, what is my list of inputs? Good. And my outputs? 10, 16. Good. Okay, so then Jad on B, part B there, which one's my independent? Good. And what's my dependent? Good. Okay, and back to Chris, what's my list? 4, 10, 25 for my inputs. My outputs are 15, 12, and 15. Good. Okay, C. What is, Taylor, so what in this one, what's my independent variable? B, yeah. B, because B's what? B's X there, right? The first thing. Good, so what's my dependent? C, little c, good. Josh, what are my list of B's? 3, 4, 5, 6. Yep, 3, 4, 5, and 6. And what's my list of, Josh, what's my list of outputs? 7, 11, 15. Yep. Okay, good. Alright, let's look at class example 3. Alright, the diagram shows relations expressed in different ways. In each case, state that an independent variable states a dependent variable. So, just looking at it, all you're doing is saying independent and dependent. That's all we're doing. So my independent, my dependent, independent, dependent. Okay, Breezy, what's my independent variable for A? Nope. R, because when I plug something for R, it gives me a C, right? So R is independent, C is my dependent. Okay, Allie, what do you think for B? It's kind of the one I was talking about with Jad. If I threw in the ball, like something depends on something. Well, how about this? Height is dependent on the time. So which one's independent? Time, right? Okay, another way how you should like automatically get it is this is what? The x-axis. We know x is independent, right? This is my y-axis. Okay. We good? Okay, and then it says the amount of, oh, that's just SAP, SAP, no. S obtained from maple, oh, SAP, I got you, it's actually the word SAP. I was like, what is that? Is that like a special formula? Okay, I'm really in math mode. The amount of SAP S obtained from a maple tree is dependent on time T. Container left attached to the maple tree. So, it's saying what's, right. Yeah. So, your independent, you said, is what? Time. And then SAP, right? Okay, that's correct. Time is independent. A lot of times, time will be independent. Okay? Your height can't determine the time. Stuff like that. It's kind of weird. Okay. Are we still okay? In this section, we'll consider relations defined by an equation and sketch a graph by plotting ordered pairs. Make a table of inputs by choosing replacements for the independent variable. So just talking about, like, you can place these on a coordinate grid in terms of investigating what your relationship looks like. Okay, we'll get to that, and then we should be done. Yeah, we'll be close. It's going to be a time crunch. No negativity. There's only one problem right here. Should go fast.
Yeah,
There's two like it. Alright, so complete the first 5 rows of the following table of values which show the possible input values. So we're doing 2x minus 5. It gave me inputs for x. So I just plug those in and I get my y's. Okay, let's plug those in and get my y's. So when I plug negative 2 in, what's 2 times negative 2? Minus 5. Negative 9. Negative 4 minus 5, negative 9. So there we are. Negative 2, negative 9. And you just continue that. Okay? So continuing that, I got negative 7. Then I got negative 5. Negative 3. And negative 1. And then I did 6 and 4. I got 7, 3. I add those in. Okay. And all that's done is just by plugging them in for x. Okay. We can probably stop after this one, probably. We'll do example 5 later or something. All right. So then plot the ordered pairs. So now we're just going to plot these ordered pairs onto our graph. So we have 2, negative 9 down here. 2, negative 7. Or no, negative. Oh, I wrote that wrong. Negative 1. This is on the wrong side. Negative 2, negative 9. Right there. Negative 1 to negative 7. Right there. 0, negative 5. 1, negative 3. 2, negative 1. And 6, 7. 4, 3. Okay, so you can see that linear relations there. It says connect the points on the grid and extend the line in both directions with arrows at both ends, which means it goes on forever. So just draw your line, put arrows, put arrows. Use a graph to determine the value of y equals y when x equals 6. So x equals 6 is right here. We already did that. We got 7. Use the equation to determine the value of y when x is 6 and verify the answer. So now to verify the answer, we would just plug it in to 2 times 6 minus 5. I just plugged it in for x. 2 times 6 is 12. 12 minus 5 is 7. So 7 is your output. Okay, we already did part F. We already did part G. And part H. Complete the following statement. The relationship is called a linear. It's a line. Linear relationship. Okay, it's called a linear relationship. All right. I'll let you guys kind of take a gander at example 5, and that'll be it for today finally.